Welcome back. Welcome back. Everybody had a good holiday break. So what we're going to do today is we're going to kind of revisit chapters 8 and 9 a little bit, and that's so that we can go over confidence intervals. One topic that we have not covered there yet. So this is going to go back over chapters 8 and 9. Incidentally, your exams have been graded. We're just waiting on a few students to complete makeups that need to be done. Once that's done, I will send the exams back to Canvas, and then we'll spend a little bit of time, probably next class, taking up the exam live so that you can see what was required. But getting back to chapters 8 and 9, we are now going to talk about confidence intervals. Very important aspect of differential statistics, especially when it comes to applying statistics. So I'll give you a few examples, and then we'll break down exactly what confidence intervals are and what they consist of. So let's say you were running a monkey sanctuary. So you were the keeper of a large different types of monkeys, and it was your job to provide for these animals. And let's say that one day there's an outbreak of monkey flu, and you need to quarantine the adults from the children. So you literally need to go in and separate these monkeys, and separate the adults from the children. And you want to make sure that you're still providing for these infant monkeys. You're still providing for these little baby monkeys. And you might remember back when you were doing your major in biology. You might remember coming across Harlow's experiment on infant attachment. And you might remember finding that the monkeys spent more time with the terry cloth mother than they did with the wire mesh mother. Now that might be a way to solve your problem, because we need to provide comfort for these monkeys. However, we are in the real world, and it might be outside of your budget at this point. After all the medicine for the monkey, after getting all the vets in to take a look at your child monkeys, after doing the quarantine, there might not be a lot in the budget left to buy terry cloth mothers, to buy enough. So in this case, you would be asking yourself, how many terry cloth mothers do I need so that each monkey can spend enough time with that terry cloth mother? So you're not going to buy a terry cloth mother for every single monkey, because they don't spend 24 hours a day with the terry cloth. Well, what you want to make sure is that there's enough, so that when they share their terry cloth mother, they can spend enough time with them. But you can't overspend, because again, you're running a business here. You don't have unlimited funds. So if you were to ask Harlow about this predicament, you would not at all be interested that the wire monkeys spent longer with the terry cloth than they did with the wire mesh mother. So that is the difference between an applied situation and an experimental situation. In an experimental situation, in theoretical psychology, it was fascinating, groundbreaking that organisms need comfort and will choose comfort more than they choose food. And in terms of attachment theory, in terms of psychological well-being of developing organisms, that was a break. That was merely that there was a preference for the terry cloth mother. To a psychologist, oftentimes the size of the preference doesn't matter. The mere existence of the preference is what is theoretically interesting. So Harlow probably wasn't interested in how much time do they spend with the terry cloth mother, or how much more time do they spend with the terry cloth mother. All Harlow was interested is whether or not they do spend more time with the terry cloth mother. However, in the real world, when you have the male adult monkey in one area of your sanctuary, and you got the baby monkey in the other area of the sanctuary, and you don't have an unlimited budget, you need to buy terry cloth mothers for these, so they have a little bit of comfort, they have these surrogate mothers. Then it becomes very important how long they spend with the terry cloth mother, because you are going to have to buy twice as many if they're spending 18 hours with the terry cloth versus if they're spending only 9 hours with the terry cloth. So again, for Harlow, it was just enough that he could find statistically that they were spending longer with the terry cloth. But in applied situation, sometimes you need to know how much time do they spend with the terry cloth mother, and that's where today's discussion on confidence intervals is going to provide us with a way of answering that question. Let's take a look at another experiment that we looked at. So we looked at the experiment on and the estimation of car crash. And we saw with that independent means t-test that the remembered speed, the estimated speed was higher if you ask somebody how fast were the cars going when they smashed into each other versus if you ask how fast were the cars going when they hit each other. So this again was a fascinating, very influential psychological finding, because it showed that memory is malleable, reconstructed, memory can change, and your recollection for an event can change depending upon how you're asked the question. So for Loftus and Palmer, and for theoretical psychologists in general, that difference was enough to show that the estimates were higher for the smashed into, and you didn't really need to think about how much higher. Was it 6 miles per hour higher, 10 miles per hour? We didn't need to know the difference because theoretically you've shown that memory can be affected by language if the estimates are higher. So all we needed was that difference. However, in an applied setting, sometimes you need to know the size of the difference. So if you were in the judicial system, if you were a psychologist that oftentimes gets called as an expert witness, and somebody mentioned that in this trial, particular manslaughter trial, one of the witnesses was asked how fast the car traveling when it violently and egregiously smashed into the truck. Let's say that's what happened during the trial. Well, we know from Loftus and Palmer that her estimate of how fast the car was going to be higher. Her estimate is going to be higher. And that's a theoretically interesting result. But for a court of law, they need to know how much higher. So you can't unring the bell. You ask this witness to disregard that question and rephrase it. The damage has already been done. So when this person says they were going 85 miles an hour, we need to figure out exactly how fast were they going. We know that she's overestimated. But by how much? They would bring in a expert witness, a psychologist would say, not only did she overestimate how fast the car was going when it smashed into the truck, but I can also tell you by how much she overestimated. And whether or not it's criminal or not criminal might depend on whether or not the psychologist says the overestimation was 15 miles an hour, or it was only 5 miles an hour, or the overestimation was 20 miles an hour. Those differences can affect whether or not the outcome of the trial. So again, we have a situation where up until now we were hypothesis testing whether there was a difference or whether that was not statistically significant. That was the big decision that we were looking at. However, there is a lot of especially in applied psychology, where the size of the difference is important as well. And I'll give you one last example of this. Let's say that you go into industrial psychology, and you are called by businesses to improve the efficiency and productivity of their workforce. And let's say that the very big corporation of America calls you in one day, and they are asking you to tell them about that timeout study that they heard about. So timeout works for children. And let's say that they read that study and they said, you know what, timeout works as well. And we're thinking of implementing a timeout procedure for our workers. They make a mistake, we'll give them a timeout penalty. And we're going to institute either a 5-second timeout penalty or a 10-second timeout penalty. And we need to know how much more accurate a 10-second timeout condition. Because making the changes are going to be expensive. And also you are giving your employees twice as much time if they're in timeout, they cannot do work, if they're not being productive. So you have to balance as a business person the cost of making the changes, implementing this accuracy program. And you also need to make a decision based on how much more accurate is that 10-second timeout condition. So is it going to be more accurate enough? The cost benefit analysis means that your workers are more productive in the 10-second timeout condition. Or does the accuracy not offset the loss of that extra 5 seconds, the loss of that timeout condition? Does it not offset that? And again, for a psychologist, all we're interested in is that the 10-second condition was more accurate. But a business person might say to you, I don't care if it's more accurate in the 10-second condition. I need to know how much more accurate. Because if it's only 5% more accurate, then our number crunchers have told us that's not going to be a profitable change to make. We're going to stay with the 5-second timeout. But if it's more than 5% more accurate, then we are going to make the change. So I don't need to know that it is more accurate. They need to know how much more accurate. They need to know an interval. And as we're going to see, that basically boils down to a confidence interval for that estimate. So what we're going to do today is we're going to do an overview of confidence intervals. We're going to go over what estimation is. We're going to go over how to construct a confidence interval, what the basic parts of a confidence interval is. And then next class, we're going to take a look at how to actually calculate using SPSS. So today is going to be a more theoretical introduction, easy introduction into what a confidence interval actually is. All right, so an overview of confidence intervals. When you're asking about how big something is, when you're asking about the size of the effect, what we're asking about is an estimation. So an estimation is an inferential statistical procedure, so still inferential stats. But it's where you use a sample statistic to make an approximate judgment for some population parameter. So it's where you take a look at your sample, and based on that information, based on those raw scores, you make an estimate about what is the case for the population. So taking a look at our sample of 9 monkeys and how long they like to spend with terry cloth. We make an estimate of how long monkeys in general like to spend with terry cloth mother. So that's what we're doing today. It's estimation. It's taking what you know about a sample and using it to estimate a population parameter. So two concepts that we have to get very clear to understand confidence intervals. What a confidence interval is made of. The idea of a point estimate and the idea of an interval estimate. So typically when you ask somebody to estimate a parameter in the real world, what they're going to do is they're going to give you a point estimate. So a point estimate is a single number that is used to estimate an unknown quantity. So if you are going to introduce one of your friends to your cousin that's visiting from Milwaukee, and your friend says, how tall is your cousin? You might say, I'm going to estimate it, and I'm going to say she's I don't know why that's past. She's 5'6", right? All right. That's a point estimate. That's a point estimate. It's one single number. Single number. 5 foot 6. So 5 foot 6. One number. One estimate. One estimate. One exact guess. What her current height is. Current height is. And that's typically what people do in the real world. Typically when you ask people how long is it going to be? How long is it going to be? Oh, it's going to be an hour. Oh, it's going to be an hour and a half. How far away is it? How far away is it? Oh, it's about 50 miles. Oh, it's about 50 miles. They give you that one number. 1 point. It's 1 point. It's one number estimate. One number estimate of that unknown quantity. The other form of an estimate is an interval estimate. And an interval estimate is a range of values to estimate this unknown quantity. So if you use an interval estimate for the height of your cousin from Milwaukee, you might say, well, she's 5'2", 5'2", and 5'10". So you're still estimating that parameter. This time instead of using a point estimate, using a single number, using a range of numbers. So how much time is it going to be? Somewhere between an hour and an hour and a half. How much is it going to cost? Probably between $200 to $300. Right? How far away is it? It's between 50 and 60 miles away. So these are all interval estimates. Where you use a range. And you're hoping that in that range is the actual truth. Somewhere within that interval is the actual true value that you're trying to estimate. So we have point estimates. We have interval estimates. Interval estimates kind of foreshadow. Your confidence interval is made up of those. Both of those. It's made up of a point. And around that interval, you have an interval. So it's important to have an idea of what these two estimates are. But the two estimates have very characteristics in terms of precision and in terms of confidence. So the point estimate is an estimate that has high precision. So you're being very exact. You're being very precise in terms of what you think the parameter is. So if you say your cousin's height is 5 foot 6, that's your estimate. That's a highly precise estimate. You're not saying 5 foot 7, 5 foot 7, you're not saying 5 foot 5. Very exact. You're giving a point estimate. You're giving an exact guess as to what her weight is. On the other hand, the interval estimate has low precision. So it's somewhere in that range. Something in that interval. So that has low precision. It's not very exact. It's somewhere between 5 foot 2 and 5 foot 10. There's a wide range of values. Very low precision. Now the flip side of precision is confidence. So if you're going to have high precision, you by definition are going to have lower confidence. So if your friend who's asking about from Milwaukee, if your friend says, are you sure? She's 5 foot 6. She's 5 foot 6. You can be like, yeah, I'm pretty sure. She's 5 foot 6. She's 5 foot 6. And if they're like, are you really sure? She's 5 foot 6. She's 5 foot 6. You'd be like, no, not really. No, not really. She could be 5 foot 5. She could be 5 foot 5. 5 foot 7. 5 foot 7. Just estimating her height. So there's not a lot of confidence in that 5 foot 6. And if somebody says, she's actually 5 foot 7, you'd be like, didn't rock my world. There's not a lot of high confidence. So high precision leads to low. You are very low confidence. You have actually estimated it correctly. And the reason for that is the more precise you are, the easier it is to be wrong. So if she's 5 foot 6 and a half, you're wrong. If she's 5 foot 6 and a quarter, you are wrong. You are wrong. If you estimated 5 foot 6, highly precise. You have very low confidence. You got that correct. On the other hand, an interval estimate is low precision. So you can be very confident. You could have high confidence. That is correct. So if your friend asks you, how tall is your cousin? And you're like, well, she's between 5'2" and 5'10". And they go, are you sure? Like, yeah, I'm pretty sure. Are you really sure? Yeah, I'm really sure. Are you really sure? You might have to think about it for a second. You might say, yeah, I'm really sure. Highly confident that she's between 5'2" and 5'10" and 5'10". So with low precision, you get high confidence. Now what we're going to see today is that you can actually specify a level of confidence using inferential statistics. So if and this is tied to your interval estimate. So if your friend says, "Are you really sure?" 2 and 5'10", you can say yes. You can say yes. I have that level of confidence. If they say, "Are you really sure?" You say yes. I have that level of confidence. And if they're like, "Are you really sure?" Between 5 and 2 and 5'10". At that point, you might say, "No, I am not really sure." She's between those. And if they said, "Okay, I need you to be really sure. I need you to have that level of confidence." I don't know why they would. They have that level of confidence. At that point, you can say, "All right, I am very confident between 5'2" and 5'10". But if you want me to be really sure, let me expand the interval, because I am really sure. She's somewhere between 4.5 and 6 foot. Like I am really sure she's between. And if they want you to take the level of confidence even higher, if they want you to be like really sure, you can say, "All right, I can do that. My cousin is somewhere between a foot and a half and 18 feet tall. And I can be really positively sure. And basically, the bigger your interval, the higher your confidence goes. So we as psychologists and statisticians, we can't get away with these intuitive, really short estimates. So what we're going to see today is how to make a confidence interval, how to pick a width of this interval. So you can put a specific level of confidence on it. You could say things like, "Here's my interval, and I am 80% sure that the true value is somewhere in this interval." Or you can make a wider interval and say, "All right, with this wider interval, now I'm 95% sure that the true value is somewhere in this interval." So we can actually determine intervals that give us the confidence that we want. And if somebody says, the lawyer says, to be admissible as evidence, you need to be 99% sure. Right? We need a 99% confidence level. You can say, "All right, for 99%, I got to make my estimate this wide. I'm 99% sure." So that's what we're looking at today. Confidence intervals. How can you choose a point estimate? Choose an interval around that point so that you can specify and figure out how confident you are that the value that you're trying to estimate is within that interval. All right, this all goes back to the logic of hypothesis testing. So typically confidence intervals are when you do your hypothesis test and you put your sample in your comparison distribution, and it goes outside of the critical zone. It goes into the tails. So you know that your sample no longer belongs to the known population, to the original population. Your sample now belongs to a new different treated population. And the question often is, now that we know that it belongs to a new population, what is the mean of that new population? So we're dealing with a new mean population. And now that we found an effect, in essence, what we're asking is, how big is this effect? Right? Now that we know that the monkeys do prefer the terry clock mother, so they belong to a population that does prefer the terry clock mother. How many hours is the average? What's the average amount that monkeys spend with the terry clock mother? So confidence intervals work the same way as hypothesis tests. Just kind of next step beyond. So the hypothesis test tells us that the confidence interval belongs to the treated population. That's what a significant p-value tells us. That's what accepting the research hypothesis tells us. Our sample belongs to this treated population. But we don't know where in this treated population our sample came from. And that is why we need an interval. So that treated population much like the untreated population, much like the original population, has a comparison distribution. So once again, we are dealing with a sample, and we know that the people in this sample came from this population. That's what our hypothesis test has told us. But the question now is where did this sample come from that population? And in order to find out where a sample comes from in a population, you need to look at the comparison distribution, which is a distribution of sample mean that is now from the treated population. So we have a distribution of sample from the treated population. It's as if you took this treated population, took the standard deviation divided by the size of the sample, took the mean of that treated population. That's what we're trying to estimate. The mean of that treated population. Right? So we know that our monkeys now belong to that loving population. But we now want to know how much. You know, what's the average amount that monkeys spend with the terry cloth mother. So the challenge here is that maybe our sample came from the center of this population. In which case it would be in the center of the distribution of sample mean. Or maybe it came from this point in the population. Maybe it's in that part of the comparison distribution. Maybe we had a very unlikely sample from our treated population. Maybe we even got an extremely rare from our treated population. So if this is the case here, then our sample mean would be a good estimate for the population mean. But if this is the case, then our sample mean is going to overestimate the population. And if this is the case, then our sample mean is really going to overestimate the population. And the same thing can happen in the opposite direction. So what we need to do is we need to use this distribution of sample means, and we need to have it use its characteristics to determine a range that we can use in order to be confident at a certain level that our sample mean falls within that our population mean falls within that interval. All right. So again, challenge is we don't know our sample belongs to this population. But we don't know if it's there, or if it's there in the distribution of sample means. So we now have to come up with a range so that we can be confident at a certain level that our range built around this sample contains that population mean. All right, so to explain this, we're going to take this distribution of sample means, comparison distribution, treated population, and we're just going to expand it visually. It's a little hard to fit what I need to explain. So this is just being stretched out for visual purposes. And we have the mean of the treated population. And that is what we want to estimate. Right? So that is the mean how long do monkeys spend with the terry cloth. We don't know what that is. But that's what we want to estimate. And in our interval estimates, if our estimate contains this line, then we have estimated correctly. If our estimate does not contain this line, then we've estimated incorrectly. That line is where the mean of our population. The mean of our population is what we want to estimate. So far so good? Okay. So let's start off with a point estimate. Let's say that we measure the mean of our sample, and we use that as a point estimate. They're saying how long do the monkeys spend? With the terry cloth mother, we got 9 monkeys right here, and they spend an average of 15.3 hours. So that's going to be my guess. My best guess is 15.3 hours. That's a point estimate. And if that lines up with your population, then you've gotten it. You've estimated it correct. But remember that a point estimate has low confidence, and it's got extremely low confidence because you said they spend 15.3 hours. What if they spend 15.4? You're incorrect. So we want to make sure that our estimate contains the population mean. So what do we do? Well, what we do is we pick a certain percent of the distribution to be in the body. And we pick a certain percent to be in the tail. All right. So let's start it with 90% in the body. All right. So we got 90% in the body, and that means that we got 5% on one tail, and we got 5% in the other tail. All right, so we take a look at our distribution, and we look up our cutoff values. We say, all right, on this distribution, we got 5% in this tail, 5% in this tail, 5% in this tail. We got 90% in the body. And let's say that we choose as our interval. We choose the width of the body to be our interval. So what's going to happen if we make our estimation interval the width of the body of this comparison distribution, and the width of the body if 90% of the distributions in the body, 5% is on the tails on either side. All right. Well, we've already seen that if our mean just happens to luckily coincide with the population mean, then if we have a width that's as wide as the body of our distribution, we are going to have successfully estimated. Right? So this is a successful estimate because our interval contains the population mean. If on the other hand that was our sample mean. As a point estimate, we blew it. We've overestimated the population. Because there's our point estimate. There's our population. And we've missed. But if we add that interval that's as wide as the body, right, so now the entire interval has shifted over. Notice that the population mean is still within that interval. So even if that's where our sample happens to be, and again, we don't know where our sample came from. But if that's where our sample just happened to come from, then this interval still contains that population mean. Still estimated it correctly. Another point estimate. Another failure in estimation. We haven't estimated it correctly. But if we add the interval that's as wide as the body of the distribution. Notice again that this interval contains that population mean. We've estimated the population mean correctly. And this happens for sample after sample. So even samples that are very low in terms of their sample means, samples that are very high in terms of their sample means. All of these samples here that serve as the point estimate. As long as you have that interval around that's as wide as the body of your distribution, you can see that we have successfully estimated in every single one of these instances. So if your sample was this sample, you've successfully estimated. If it happened to be this sample, you've successfully estimated. If it happened to be this one, or this with an interval of this length, you have successfully estimated your population parameter. So in all these cases, this interval has led to a successful estimation of the population parameter. But what happened with this one over here? Well, if your sample is this extreme, right? If your sample just happens to be that extreme, and again, we don't know where our sample comes from this distribution. But if this is where our sample mean was, notice that this is the first time that we've missed. Right? This is the first time. This population does not fall within the interval that we've estimated. This is the first time that the population is not inside this range here that we've estimated. And the only time when this happens is when your sample mean comes from one of the tails. If you choose an interval that's as wide as the body, the only time you're going to miss that population mean is if one of your samples comes from the tail. And we said that we chose the width of this body 90%.
And we chose one tail to be 5%. And we chose one tail to be 10%. So 90% of the time, our samples are going to come from the body. And it's only 5 plus 5% of the time that it's going to come from the tail. So we don't know if this has happened. Anytime we're looking at a sample, we make a confidence interval. We don't know that this has happened. We don't know that we've missed our population parameter. But we know that it only happens when our sample is from the tail. And we know that only 5% plus 5% of samples are going to come from the tail. So if only 10% of the samples come from the tail, that means that they're going to miss the estimation. That means that 90% of the samples come from the body where the estimation is successful. That means that if we're looking at a sample, we have a 90% chance that it's from the body. The estimation is going to be successful. Or we have a 10% chance from the tail. It's going to be unsuccessful. In other words, we got 90% chance of being right. We have 90% confidence. So the size of the interval is the body of your distribution, and as much of the body as you put into the interval. That's how confident you can be. That's your level of confidence. If you make an interval as wide as 90% of the body, then you are 90% confident in that confidence interval. If you make it 95%, make the body 95% of the interval, then you're 95% confident. Basically, if you shrink the tails or if you grow the tails, you can change your level of confidence. Because only time you miss with this interval is the times when your sample just happens to come from the tail. And we can determine what percentage that is by determining the size of the tails. All right, so that is the idea of the confidence interval. So now let's take a look at a little bit of the math behind it. Next class we're going to take a look at PSY. But it's a good idea to where this interval is coming from. And in terms of figuring out the confidence intervals, it's just really a matter of doing a little bit of algebra with your formula for your t statistic. So the t statistic equals your sample mean minus your population all divided by your estimated standard. So we've seen this over and over again. Statistical term. This is your t statistic calculation minus your population mean, aka your comparison distribution, all divided by the estimated standard error, aka your comparison distribution, standard deviation. Notice that in this formula, there's the thing we want to estimate. So we want to estimate population mean. And lo and behold, population mean. We don't know what it is. But there it is in the formula. So what we do is we isolate for population mean. We do a little cross multiplication. We bring population mean over to the other side. Change the sign from negative to positive. We then take the t statistic standard error, we standard error, to the other side for the sample mean. And then because the t statistic is positive and negative, you can change that minus to plus or minus. And there is the formula for your confidence interval. So your confidence interval equals your population mean. Your estimate for the population equals your sample mean plus or minus the t statistic, the critical t value times your estimated standard error. All right. So once again, we're back here with our distribution. Let's just zone in on one of those confidence intervals right there. So we got population mean. That's what we're trying to estimate. That's that value right there. Population mean equals your sample mean. So this is important to remember because your sample mean. That right there. That's your point estimate. That's your best guess. So somebody didn't want to range. I don't want an interval. Just one number. Give me one. That's going to be your best guess. That's your point estimate. That's the center of your confidence interval. interval. It's your sample mean. So the sample mean is what the entire confidence interval is based around, built around.
It's the center of your confidence interval.
However, we still got a range. And the length of that arm there is plus T times your estimated standard error.
And your T statistic,
that's your critical T. That's your cutoff T score. That's the T-score that's going to put 5% into the two tails. Remember going back to the appendix, the T statistics, those values where there's 5% in the tails, there's 10% in the tails, 20% in the tails, 1% in the tails, 1% in the tails. That's where you get that T statistic right there. That's your T critical. Estimated standard error, we get that from
standard deviation of the sample,
and that is your confidence interval. So again, we got population mean. What we're trying to estimate. That equals your sample mean.
The mean from your sample.
Plus or minus the critical T statistic
multiplied by your estimated standard error.
And it's this critical T statistic that changes that makes your interval bigger or smaller. So if you don't have to be as confident, then you could put more of your distribution in the tail, and you only in this case have 70% confidence, and you do that by changing the critical T. Where your lines in the sand are. If you need more confidence, you shrink the tail by increasing your T critical, and you can see that the size of your interval is going to get bigger,
and bigger.
That's how you
determine your confidence level.
So somebody says, I need to be 70% confident. It's a weird number to pick, but I need to be 70% confident. What you need is you need to find that T critical that puts 15% in one tail,
and 15% in the other tail.
Now we're going to be doing that in SPSS. SPSS allows you to make confidence intervals of any size. So if somebody bizarrely wants you to be 87% confident in your estimate, then insurance agency that did the math and found out that that's their break-even point. Who knows? We'll see how to do that for those exact levels.
All right, so to wrap this up for today, just to put some numbers on it.
Let's say that this was again the mean. We're looking for what the mean is. We have a sample mean of 100.
We got plus or minus 11.5.
If that's the actual mean of the distribution, if that's the actual population, it would have a mean of 100. And the tails would be at plus 11.5. So 111.5. It would also be at minus 11.5. 88.5. That's how large the tails would be. And you can see that any estimate that is plus or minus 11.5, any sample that comes from the body that is plus or minus 11.5 will contain that population. So here we have a sample that had a mean of 100. Interval goes from 88 to 111.5. That's a successful estimate. If the sample mean was 105, you add 11.5 to that, you subtract 11.5 you go from 93.5 to 116.5, still contains the population mean of 100. A sample mean of 95 still contains a sample mean of 100. A sample mean of 110 still contains, almost misses, but it still contains the sample mean of 100. And as long as those sample means come from the body, they will contain that population. So you can be confident as the body of this distribution as the percentage of the body of that of the body of that distribution is. That's how confident you are. Because you control the size of the tails. And it's only when that sample mean comes from the tails that you are going to miss. Your interval is going to miss that population. So if you only have 10% in your tails, you only have a 10% chance of missing that estimate. You can be 90% confident that you hit it. If you only have 1% in your tails, you only have a 1% chance of missing that estimate. You're 99% confident that you missed that estimate. So these confidence intervals, these exact sizes of your interval, they are determined by the size of your tails, and that limits the risk that you have. And again, by shrinking those tails, you get more confidence because you get a bigger part of your distribution is in the body. By making the tails bigger and shrinking the body, your interval shrinks, and you get less confidence. So confidence is tied directly to the size of that interval. All right. So any questions on that before we wrap up what I wanted to cover for today? It's all good. Okay. So next class when we meet, I'm gonna do a judgment call. Hoping to take up the exam next class. But again, we need to finish off a few makeups before that. But next class will also be jam-packed. So I might say the take up of the exam for the final week. Because next class, what we're gonna do is we're gonna go through calculating confidence intervals for the one sample. We're going to go through calculating confidence intervals for the dependent means t-test. We're going to go through calculating the independent means for the independent means t-test. So we got 3 t-tests to go through. We got 3 confidence intervals to go through as well. We're going to be doing stuff live with SPSS. So it's going to be a jam-packed class. So we might we'll see how it plays out. But we're definitely going to do the confidence intervals. So come here, when you get in, open up the SPSS, Excel sheet for that day. Hit the ground running, and things are going to move pretty fast. Other than that, if there are no further questions, that's all that I wanted to cover for today. So this was a bit of a ease us back into stats following our weekend. But if you have any questions or anything, if you have any stuff from previous assignments that you want to ask me about, feel free to. Other than that, that's what I wanted to cover for today. So if you're all staffed out, feel free to call it an early day.